Okay, so we have our A5 Galilean and special relativity questions. And so number one has a spacecraft moving with a speed v relative to Earth, going pretty fast, I'm sure. Passes Earth on its way to a planet. When the spacecraft passes Earth, the clocks on Earth and in the spacecraft show 0. So they synchronize at that point, but then the spacecraft is moving. So it's a moving inertial reference frame with respect to Earth. We'll call Earth the frame Earth S, and we'll call the spaceship S prime. And so S will just have normal Galilean transformation, but for the spaceship, we'll have relativistic changes. And so the Earth clock reading as time passes, if v is d over t, then the time reading will just be the distance divided by the speed of the spacecraft, that speed as measured from Earth. But then the spacecraft will have a dilated time based on its speed, based on the Lorentz factor gamma, which in the data booklet is given as radical 1 minus v squared over c squared. The time dilation equation is delta t is gamma t naught, where t naught is in the original at-rest inertial reference frame, which we'll just call that t. And so the delta t we'll call t prime. And so we wind up with t prime is t times gamma. And we just established that t on Earth is d over v. So we have the spacecraft clock reading as d over v times radical 1 minus v squared over c squared. And we have choice A. Number two, they get right into it with the Minkowski spacetime diagrams with two reference frames, S and S prime. Fun. So just as a reminder how this works, the frames for, or the graph, the diagram, I should say, for the S prime is tilted away from the main axis by this angle theta, and that angle must be the same. And based on that angle, we can get the speed of the second inertial reference frame by tan theta is v over c. And the scale for ct prime and x prime is not the same as for ct and x, so remember that. Also keep in mind that the x-axis is position and time is the y-axis, and it's not even time, it's speed of light times time, so that it has the same units as x. So it's possible, for instance, to have a light pulse travel to the left and up because it's not going backwards in time. It's impossible to have anything go down below the x-axis that would be going backwards in time. You can have events below the x-axis as what has happened in the past, but something can't travel down below the x-axis because that'd be going backwards in time. Speaking of events, we have events plotted on our co-diagrams, P, Q, and R. And so we have Earth, which is going to be our at-rest reference frame, and then we have the spaceship, which is going to be our moving reference frame. Now it's asking about the spaceship, and so we need to plot these points, or graph them according to the grid, I should say, of the S prime. So basically, I'm going to draw lines that are parallel to the axes for S prime. I'm going to use color for this. So with blue, I've marked the grid for position for S prime, and I can see that Q and R are on the same position line for S prime. So Q and R happened in the same place. And while that's cute, it's not asking about that. It's asking about the order. So we'll use green for this. The order of the events, meaning time. Not where they happened, but when they happened. Time axis. So yeah, looking at the time axis and drawing parallel lines for the time axis to see where events occur, or when events occur, I should say. I can see that P and R are on the same line, so they happen at the same time, and Q is earlier as it hits the time axis, giving us choice D. P and R are simultaneous, but Q happens earlier as viewed from the spaceship. for what it's worth, looking at the S reference frame, the Earth reference frame, that is not tilted, I can see that P and Q are on the same line on the same horizontal line that intercepts the CT axis. So according to Earth, P and Q happened simultaneously. So it's a good example of simultaneity, that simultaneity can't be true in both reference frames if the reference frames are moving relative to each other, close to the speed of light. So for number 3, we have two frames of reference, x and y, and we know that the formula for velocity addition, relativistic velocity addition, is u prime is u minus v over 1 minus uv over c squared. But this formula is set up for if the inertial reference frames are traveling at relative speed but in the same direction. In this case, they're traveling in opposite directions. And so that would mean you would need to negate one of the velocities. And so we know that v is the velocity of s prime. And so we're going to flip that around and we're going to negate v. So if we use the same equation, but we put in a negative v in for v and collect our terms and our negatives and positives, we wind up with u prime is equal to u plus v over 1 plus uv over c squared, which is choice D. Here's number 4. Okay, so here we have a relativistic velocity addition problem. We have a spaceship going 0.6 times the speed of light from Earth. That would be v, the speed of the second inertial reference frame, when it launches a probe at 0.1 c relative to the spaceship. So that's an event, and that is relative to the spaceship, so that would be u prime. And it is also moving away from Earth, so both velocities v and u prime are positive, moving away from Earth. And so what is the speed of the probe relative to Earth? In other words, what's the velocity of the event as measured from the first reference frame being Earth? So what is u? So our equation is u prime equals u minus v over 1 minus uv over c squared, and that is on the data booklet. It is there, all right? So we're looking for u. We have u prime as 0.1 c. We have v as 0.6 c. So it's a little weird, like we're solving for u, so we have to collect our terms. But when we collect our terms and solve for u, we do wind up that u is 0.66 c. And that is choice B. So we have ourselves a Murkowski, I forget the guy's name, space-time diagram. And so we have two reference frames, both S and S prime, shown in the diagram. All right, and so the question makes reference to a event X. So the event X is right here, and that occurred in the S reference frame. And it says which event occurs at the same position, not time, position, in the S prime reference frame as X. So they would be on the same world line as relative to the S prime frames. So we draw parallel lines to the S prime frame. So let's do that. And actually, before we do that, I just wanted to comment about the S frame. And I can see that events A and B are the same position as X. Position as X in the S frame, because A and B are on the same line for position in the S frame. But it's not asking about the S frame, is it? Now remember that the actual, the grid for the S prime frame is bent just as the grid, as the axes are, based on that angle. Remember, you can get the velocity of the frame from that angle, where tan theta is v over c. V would be the velocity of the second S prime reference frame. but we don't need that for this problem, but that is why the S prime frame axes are kind of squeezed in that way. And so if we were looking at time events in the S prime frame, we would draw lines parallel to the X prime axis to see where it intercepts the CT prime axis. And so everything that's on these lines would happen at the same time, would be simultaneous according to the S prime frame. But it's not asking about the same time, it's asking about the same position. All right. Okay, so I drew my parallel lines to show the intercepts on the X prime frame, and I can see that X and C are on the same position line for the S prime frame. So what's in the same position as X? That would be C. C is in the same position. They didn't ask. Why did I highlight in blue? I'm using red for position. Be consistent. Okay. And so they didn't ask, but notice that B and C are not on the same position line, but they are on the same timeline as measured in the S prime frame. They do not happen in the same time or position in S frame, but they do happen at the same time in the S prime frame. But they didn't ask about B and C. They asked about position, and so the answer is C. Okay, number 6. We have a spaceship leaving Earth going 0.6 c relative to the Earth to a point P. P is 3 light years away. Spaceship returns to Earth. Ignore the time taken to reverse the direction of the spaceship. What's the time taken for the total journey to and from P as measured by an observer in the spaceship? So this is going to be a time dilation problem, where the dilated time is given by gamma times the proper time. Now here's the kicker. That delta T naught, that's the proper time as measured by the moving inertial reference frame. The time is measured by Earth by the stationary frame. And so we can figure out that time is measured on Earth by just a simple, speed is distance over time. And so the time would be 3 light years divided by 0.6 times the speed of light. That turns out to be 5 years. Don't forget it's round trip, so 5 years times 2 is 10 years. And so that 10 years right there, that's the delta T. That's not what we're looking for. But we're going to need it in order to find delta T naught, which is the proper time as measured on the spacecraft. So basically we got to figure out gamma, and gamma is given in the data booklet, or what we call the Lorentz factor. The gamma is called the Lorentz factor. That's 1 over radical 1 minus v squared over c squared. And so the speed of the spacecraft is 0.6 c. And so when you square that, we get 0.6 squared times c squared. And so the c squareds cancel. So I have 1 minus 0.6 squared, square root that, 1 over that whole thing. In the end, we get 1.25 for our gamma. And so going up to that proper time, if the dilated time is gamma times the proper time, then proper time is dilated time divided by gamma. So that's 10 years over 1.25, and we get 8 years, which is choice C. And so QBank only gave me 6 paper 1A questions, but I think it's a good sample with both using the equations and also looking at space-time diagrams. And so now let's dive into the paper 2s with numbers, this number 7 from that specimen exam with a flying spacecraft. So the first question, 7A, wants you to solve for the Lorentz factor, gamma, for a speed of 0.8 c, and gamma in the data booklet's given as 1 over radical 1 minus v squared over c squared. And so the speed of the spacecraft is 0.8 times the speed of light, so we put that in for v, and we get a Lorentz factor of 1.67, which agrees with the bark scheme. Then for B, it says first, find the distance between the light pulses from the reference for the reference frame of the spacecraft, so that's S prime. And so X prime, the distance between the pulses, is gamma times the actual distance as measured from the space station, minus the speed of the spacecraft times the time, but the time from the space station's point of view is that the lights were simultaneous. So t would be 0, and so the vt aspect drops out, and so we just have 1.67 times the length as measured from the space station, which gives us 2,000 meters. And that agrees with the mark scheme. And then for BII, instead of the lengthened position between the light pulses, now we're going after the time. So for number 7, 7a wants the Lorentz factor, the gamma value for 0.8c. So we use from the data booklet that gamma is 1 over radical 1 minus v squared over c squared, and we get 1.67 for gamma. Then B wants the, for the reference frame of the spacecraft, that would be S prime, the distance between the light pulses. So we could use the Lorentz transformation for position. X prime is gamma x minus vt. X is 1,200 meters, that was given. That's the distance for the space station. And so vt would be 0.8c times 0. Since the pulses were simultaneous, as viewed from the space station, the time between the pulses would be 0, so that VT factor is gone, and we just have 1.67 times 1,200 meters, giving us 2,000 meters. And so that is BI, and then that's the relativistic distance, and then BII wants the relativistic time. So we use the time equation. T prime is a gamma t minus vx over c squared, and v is 0.8c, x is 1,200 meters, gamma is 1.67, and so our time actually comes out as negative 5.3 times 10 to the negative 6 seconds. And so the negative comes into c, where it says determine which light pulse happens first, and since that relativistic time is less than 0, it's negative, that means that the further point happened first, which also makes sense because the spacecraft is approaching F and receding from R, so it would receive its light pulse from F before R. And so that's 2 points. To say that the T prime is negative is the first mark, and then the second mark says that F happens first. So that is 8. Then we have that's number 7. Here's number 8. And this actually says that this is from a previous question, so there are some things that are not in it, but it says observer B is moving at 0.6c with respect to a space station at rest. Observer A at rest on a space station. So observer B is S prime, and the observer A on the space station is S at rest. And it says write down the length of the space station according to Galilean relativity, which means no relativistic shifts. It's 100 meters, so don't overthink that. And so that's just 100 meters. Then it says define what is meant by proper length, and that's the length measured by an observer at rest with respect to whatever you're trying to measure. So that's a good definition. I kind of know that guy, right? Then BII says calculate the length of the space station according to observer B, who's moving with reference to special relativity. So we can use the length contraction formula for this, where L is equal to proper length over gamma, and gamma is, of course, 1 over radical 1 minus v squared over c squared. The speed is 0.6c, I believe it said that, moving at 0.6c, so that's where that comes from. And we get a Lorentz factor of 1.25. We throw that into the length contraction equation, and we get 80 meters for our space station according to observer B. And then C doesn't actually say how the results contradict Newton's postulates about time and space. And the mark scheme says that's not in the syllabus. But I think that the Einstein's postulates are. So I don't know. But anyway, Einstein's postulates are that, here, let me kind of write this down. Einstein postulates of special relativity. 1, laws of physics are the same in all inertial, non-accelerating, inertial reference frames. And then 2, speed of light is same in all inertial reference frames. Don't write IRS. I'm writing that here to save space. But that's not what they asked for. They asked for Newton's, but they're like, how do the results contradict Newton's postulates? Because they're relativistic. They're Einstein's postulates. So there you go. That is number 8. Now, number 9 is the next question, and I'm going to pause it. Okay, so we have 2 events, objects, whatever, A and B, and it says that relative to the ground, to reference frame S, the velocity of A is 0.6 c. We can call that the S prime frame, so to be V for the velocity of S prime. And then we have another object, B, which can be like another event having a velocity U of negative 0.75 c headed towards A. And we can call that U, the velocity of that event. And it says what is the velocity of that event B relative to particle A, which is S prime. So that would be U prime. So we have an equation for this. U prime equals U minus V over 1 minus UV over C squared. So we plug in all of our numbers, we eliminate the C's in the denominator, and when you work it all out, we get negative 0.93 C, which agrees with the Mark scheme. And then the second part says, particles are emitted at the same time according to observer X at rest with respect to the ground. Another observer Y is moving parallel to the ground, so Y is moving. B, show that the particles are not emitted simultaneously in the frame of observer Y according to the Lorentz transformation equation. So the observer Y is moving, whereas observer X is not. And so if X says they're simultaneous, because of the rules of simultaneity, Y, they're not going to be simultaneous for Y. But it's actually saying, how do we know that? It says, use the Lorentz transformation equations to show this. So if we're talking about simultaneity, or when the events happen, so we're looking at time here, and so the Mark scheme says, use the Lorentz transformation equation for time. And so the Mark scheme, you don't actually have to calculate the difference in the time. You just have to show that the time is not simultaneous. And so when we say that the time is simultaneous, that would mean that's where they're getting this time right here is 0. That's what the simultaneity means. But the fact that we do have a gamma factor, there's our gamma factor from the data booklet. Since there is a gamma factor, then we know that T prime is not also 0. And so therefore we can conclude that the delta T is not 0. What it is doesn't matter. We can just show that it's not 0. So therefore it is not also simultaneous. Number 10, we have ourselves a space-time diagram showing 2 inertial reference frames, S and S prime, and then S, the inertial reference frame S, is the regular axes for X and CT, and then we also have the axes for S prime with X prime and CT prime. And of course, they are squeezed because if that frame is in motion, then the axes are tilted with respect to the vertical and the horizontal. We can remember that those 2 angles are the same, and we can actually get the velocity of S prime from that angle. So you can say tangent of theta is the speed of S prime V over C, and so I can see based on that triangle, opposite over adjacent is 4 over 5. Based on the triangle, I can show you. So there's the triangle that I'm talking about, opposite over adjacent. Keep in mind I can't also use the hypotenuse there because it's on a different scale. You can be like, oh, look at that, the hypotenuse is 3. No, it's not, because the scales are not the same for the 2 different frames. And so in the end, we get that the velocity of S prime is 0.8 times the speed of light, which agrees with the Mark scheme. Ooh, look at that. The problem continues. It continues a lot. We have B, BI, B double I, B triple I, BIV, and then it goes to 11. All right, let's keep going. So here we have, for an observer A at an event that has space-time coordinates of x equals 3 and ct equals 1, plot the point corresponding to the event on the diagram, label the point E. That's easy. Let's go back to the diagram. Here it is, point E, x equals 3, ct equals 1. And I'm reading the question and I'm like, who the heck are A and B? And it says it right in the beginning of the problem. So I'm talking about S and S prime, so let's define that, maybe more for myself than for anyone else. All right, so the axes for A are the regular axes, and the axes for B are the space-time shifted axes. And yeah, observer A is in the regular S inertial reference frame, B is in S prime. So B double I says, according to B in S prime frame, event E occurs before observer A and B meet. So yeah, here is the line for E parallel to the x prime axis to see where E would intercept with the ct prime axis, and it looks like it intercepts at about maybe negative 2.3 or somewhere around there. But yes, that is in negative time. So if we go back to here, E occurs before A and B meet. Yes, that is a negative time relative to the origin. So yes, E does occur before A and B meet. And then it doesn't actually ask for a number, but it does say, accept use of Lorentz transformation to show that ct prime is negative 2.3, which also makes sense from the intercept. And so you can figure that out using Lorentz transformation or actually look at the graph. Now it says, what are the spacetime coordinates of the event according to observer B? Well, we've already established that the velocity of B in S prime, or S prime, the frame itself, is 0.8 times the speed of light. And they say there's two different ways of doing it. You can do it using the diagram or using Lorentz transformation. So let's look at the diagram. And this is 3 marks. So it gives a mark each for the lines, and then a mark for the answer. And so we can see, based on the diagram, this is really annoying how we have to go back and forth, apologies. But we can see, based on the diagram, that by drawing parallel lines to the axes for S prime, we get that the position, did I say X prime? For S prime, not X prime, S prime for observer B, we get that the X prime position is about 3.5, and we get that the CT prime for the time is negative 2.3, which agrees with the mark scheme where it says that the CT prime is between 2 and negative 2.75, and that the position is between 3 and 4. And so again, we got negative 2.3 and 3.5, so that works. They said alternatively, you can use the Lorentz transformation where they calculated gamma. Again, as a reminder, the formula for gamma, as given on the data booklet, is 1 over radical 1 minus v squared over c squared. And when you run that all together, you get 1.66666 or 1.67, depending on how you round it. There's our gamma. So we can find our CT squared, our CT prime, by using the Lorentz transformation for time, which they got negative 2.3. And then you can get position using the Lorentz transformation for position, which winds up giving us 3.7. So you could use the equations if you want. I personally like using the diagrams. That's the whole point of the diagrams, right? And also the question has a diagram, so why not use it? And then they say, as a third alternative, you can actually use the invariant equation showing that they're showing space-time invariance between the two different frames. You can do it that way. I think that's the most awkward way of doing it. I personally like the diagram. I also think that's why they had alternative 1, because it's the best way. Who says it's the best way? I say it's the best way. Oh my goodness, this question keeps going. All right, so BIV. Show that the space-time interval is invariant. What? I don't want to do that. All right, let's look at the invariance equation. Okay, so space-time interval, what the heck are they talking about? And what do they mean that it's invariant? So if we look at the equation on the data booklet, the space-time interval is the time factor squared minus the position squared, which we know is actually condensed from including both y and z in three-dimensional space, but we can just represent it as one-dimensional for now. And so that's the space-time interval for S, or observer A, and then the space-time interval for B in S prime is delta S prime, S being lowercase s for space-time interval, not uppercase S for reference frame. I know. And then the C delta T is the CT, the time position for B is C delta T prime. And then the actual position X is represented by a prime for that reference frame. And what space-time invariance shows is that these two space-time intervals are the same despite the relative motion of the two different frames. They are invariant, they do not vary. So therefore, based on the CT coordinates and the X coordinates of each reference frame, if we square them and subtract them, they should be equal to each other or close. I think they're going to be close because if we're actually pulling these numbers from a graph based on where lines intercept, the values are not going to be precise, but let's give it a go. The time, the CT for S and observer A is 1, and then the position for observer A in S is 3. So we have 1 squared minus 3 squared is equal to, all right, so we have the CT prime for B and S prime is negative 2.3, and the X prime is 3.5. So it's close. I saw that coming. It's negative 8 is equal to negative 7, so it's close. But it's close because of how the lines intercepted on our Minkowski space diagram, right? So those were kind of like ballparks. If we actually use the numbers from the Lorentz transformation, that, where was that? I'm all over the place on this mark scheme right now. Give me a sec. Here they are. All right, so yeah, they said that the CT prime is negative 2.3, which does match what we said, negative 2.3. But they said that the X prime is 3.7. So let's try it with 3.7. So a little erase action here. Boop, boop, boop. Let's do 3.7 instead of 3.5. And a little erase action here. Let's use the red eraser. You have to make those noises when erasing. All right, so yes, it works if you use the numbers that you get from doing Lorentz transformations and not from reading the graph. So I guess the takeaway from this last question on number 10, so if you're using numbers from the Minkowski diagram and you're trying to prove space-time invariance, the numbers will be close to each other. They're probably not going to be exact. I'm sure that is perfectly fine for the reader, whoever's reading your paper, because that is the way to do it. It even says allow error carried forward from BIII. So even if you did, like you had like a crappy diagram and you misread the diagram or something, they allow error carried forward, so I wouldn't sweat it. All right. Okay, so there are 4 more questions. There's 11 through 15, 4 more paper 2s, I should say. So you can see that here. But we're now at 35 minutes on this video, so I'm going to cut here and then come back for video 2 of 2, numbers 11 through 15, on our Relativity A5 solutions for papers 1 and papers 1A and 2. All right, thank you. See you next time.